In this year's L3 applications, the mission is to make a drone fly, but first, we need. The task is to get a quadcopter to take off and hover above the starting point for at least a second, then fly at 1.5 meter above unknown terrain where there is an unknown obstacle between 0.5 and 2 meters long, and hover for at least a second above the landing point, which is 6 meters away, and land on it. All this while optimizing the cost function by minimizing flight duration and deviation from optimal flight path. We split our path planning into 4 main stages. First, taking off and hovering. The drone will take off with an instantaneous velocity of 1 meter per second and decelerate constantly within 3 seconds to 1.5 meter above ground. This prevents the drone from overshooting the intended height and also minimizes the time for takeoff. In pre-obstacle stage, knowing that the obstacle will be at least 1.5 meter away from the starting line, and to prepare the drone for any abrupt height changes in the obstacle phase, we have similarly programmed the drone to fly at a full instantaneous velocity of 1 meter per second, which accelerates to a reasonable speed of 0.4 meter per second. In the unpredictable obstacle stage, we have chosen to implement the neural network. This form of machine learning will be explained later, but first, it is important to know that for it to function, we require sampling data's velocity and height from flight simulations to train the neural network. This stage in a training flight simulation was programmed by designing the Z and X velocity as functions of height deviation. Besides ensuring the drone maintains an ideal height of 1.5 meter, we also ensure the drone does not pitch too much for reliable height data. The more sampling data available for training, the better results the neural network will output. These training objects are fairly random. Length and positions were randomly generated within the defined ranges, while complexity was formed using ramps, steps, and pseudocircular curves. MATLAB was used to assemble random combinations of the objects, and due to the tedious process of converting these ramps to 3D CAD models, we repeated 5 flight simulations for each of the 6 most relevant ones for training. We assumed the post-obstacle stage as part of the obstacle stage as well. Finally, the last stage of hovering and landing involves the drone descending vertically at a constant velocity of 0.1 meter per second. We chose to integrate artificial neural network for the intermediate stage of alternatives such as PID control for its ability to implicitly identify complex relationships between inputs and outputs, its self-adaptive nature and flexibility. Since we are only able to sample the environment behind the drone, the neural network provides us the power of forecasting the unknown. So how is this implemented? First, we needed a library called TensorFlow for performing fast numerical computations using data flow graphs. The centerpiece is a network class called net, which we use to represent our neural network. The following list contains parameters describing the network architecture such as the number of inputs, outputs, hidden layers, and neuron per layer. The weights connecting each neuron in one layer to every neuron in the following layer and the individual neuron biases are initialized as random matrices. A core feature of the code is feedforward propagation, which, given an input, returns a corresponding output intensity following application of nonlinear logistic sigmoid function. Backpropagation is then invoked to iteratively adjust and update the weights and biases according to the gradient descent of the cost function. This allows matching of required outputs to every input set, obtaining a global optimum solution. To train our neural network using an ample dataset from simulation, we imported our neural network in a second main.py code, which accepts train and solve for a set of inputs as command line arguments. Finally, we imported the Python subprocessor library in our navigational script, enabling it to call the readily trained neural net at each instance and retrieve adequate motor output. Specifically, neural network enables sampling of terrain height at every instance to be used to accurately predict future topography. Interpolation between these points allows us to find an extremely good approximation of the terrain height directly underneath our drone at every single instance. This minimizes offset of height measurement due to a gentle slope or a null, compared to assuming a consistently flat terrain or accurate pass height measurement. Unfortunately, Testing Terminal was unable to run the ANN due to the lack of supporting computational tools such as TensorFlow. TensorFlow is an essential supporting tool to normalize sampling points in the ANN. Therefore, the actual flight was conducted using the basic navigator script without optimization from the ANN. Although the results without ANN completed the assigned mission, it can be further optimized if the ANN is deployed. To analyze the potential optimization performed by the ANN, a comparison between simulation with and without the ANN was made. By comparing the flight path trajectory, it was observed that the ANN minimized the height deviation, hence improved the overall merit function. However, it is still incapable of optimizing performance across an abrupt vertical height change. Following a thorough review of our design process and final test results, we identified limitations of the neural network and key areas of improvement for future iterations. Firstly, the neural network is only suitable for smooth displacement changes and is unable to anticipate abrupt changes due to the time lag in identifying present location. With more extensive training, the neural network's ability to deal with these abrupt path changes will improve, shortening its reaction time. However, completely eliminating time lag is impossible with so reliance on the neural network. Due to time constraints, the neural network could only be trained over 6 ramps. With the creation of more ramps, a more comprehensive set of data could be collated, with specific focus on ramps with abrupt height changes to ensure not only quantity-wise but qualitatively competent training. Lastly, our training program only designed functions for x and z velocities. Implementing control of the y velocity can be further included to ensure the drone flies in a straight line path. And this has been brought to you by Group 4. Thanks for watching.